So my talk will be divided as the title indicates into three main parts. I will remain in the generalities. I will not go into really details because I don't know the background of the professors and the students and the level. So I will go into generalities. First, I will discuss what plasma physics is and the main applications. Second, I will focus on nuclear fusion. And basically, I will focus more on what we call magnetized plasmas, basically using the tokamaks or accelerators as means to make fusion. And thirdly, I will briefly really just advertise about our efforts to have a community in the Arab world to enhance fusion research, plasma physics and fusion research. So just in case, I apologize if it is really too broad, but I think maybe it's important. So what is a plasma? Plasma is a fourth state of matter. So we go from solid to liquid by heating up the solid, and then you go from liquid to gas by heating up the liquid, and then you go from gas to plasma by also applying heat. The reason why I am insisting on applying the heat is that each time we as humans apply heat, we need to pay for it. So it costs money, it costs efforts, okay? So that's why most of the fusion plasmas on Earth are basically man-made plasmas, okay? Not natural ones, but we will come back a little bit to it. So it's important to keep in mind that plasma is something that is obtained. So it has basically, as Dr. Abdo just mentioned a little bit, so it has the properties of a gas, but in addition, it's now a gas, what you call a two-fluid gas, electrons and protons, with different masses, okay? And certainly different charges. So you have the charges come to play, and thus you have to apply Maxwell's equations. So how to obtain a plasma? Well, we said we're gonna ionize neutral gas. So we start usually with a neutral gas. We give it energy. If the energy is high enough to ionize one electron, so basically one electron will leave the orbit, and so we will have an ion which is positively charged and one electron which is negatively charged. Now, the energy that we supply can be either mass, using mass particles, or massless particles such as photons or electromagnetic waves. So this is on the way to form plasma. Now, of course, we have what we call recombination, and the recombination is the natural tendency for electrons to come back to the ions and to form neutral atoms. So you see that you have here ion plus an electron. It gives me an atom. Most probably this atom is in an excited state, so it will emit a photon to come back to its ground state. So these are the two major components of when we make plasma. One is ionization, so we give energy, and the other one is recombination. That is coming naturally. We don't need to do anything. The plasma will come, the electron will come naturally back to the ion. Now, so what is the main control parameter that allows us to have more of ionized species than for neutral species? The main control parameter is the temperature. Okay, what you see here, this is a graph. You have on the x-axis the temperature in electron volt, and on the y-axis you have the cross-section area. And now you can see that you have the ionization cross-section and the recombination cross-section put on the same graph. So if you have a 1 electron volt plasma, you can see that it will most probably recombine, and the probability that you have ionization is relatively low. Now, if you go to 10 electron volt, you can see now you actually start to have a real plasma, and recombination becomes a process which is can be neglected. Please note that the x and y axis here are in logarithmic. Both of them are logarithmic, so log. And so this is what controls the plasma with respect to neutrons. When we start, usually we start with neutral atoms. Is the temperature, or basically how much energy we are able to put to heat up this gas, and thus to reach ionization and to beat recombination. But please bear in mind, these two processes are all the time occurring in plasmas. And of course, it depends on the temperature of the field. So the density of the plasma and the temperature gives us a wide range of applications, which is going to be my first part. So here there's a summary. On the x-axis, we put the number density, which basically the density of the plasma, and on the y-axis we put the temperature. And so you can see that, for example, the aurora borealis, we'll come back to that, is occurring at a very low density and low temperature, whereas magnetic fusion is occurring at relatively higher density and high temperatures. Inertial fusion is extremely high density and extremely high temperatures. Of course, the core of the sun, that's a solid core, is extremely dense, but actually it's 10 to the power 8. You can see that in this graph, actually, I'm just noticing right now, is that the highest temperatures reached are inside the magnetic confinement device, okay? Which is basically in a tokamak here, which you see, that's the highest temperature. Furthermore, people say that in tokamaks or fusion devices, we have the biggest temperature gradient in the universe. So basically, while at the center of the tokamak you have, let's say, 10 to the power 8 degrees Kelvin, 2 or 3 meters away you have minus 270 degrees centigrade, or about 0 degrees Kelvin, or 5 or 10 degrees Kelvin. So you see that the huge difference between and 2 meters apart between the core of the plasma and it's not actually the temperature, about several Ks are inside the magnetic field generator, but spatially they are very close together, and so one has to perform very good isolation, thermal isolation, and electromagnetic isolation. Okay, so let me try to go a little bit about the applications of plasma physics. The first one, so we're going to start with the small scales and go up to larger and larger scales. So the first one is, of course, what we call plasma chemistry or plasma surface interaction. So you can see here, these are the same material. This is an example, the same material, but with different plasma properties. So these plasmas, what they are able to do, they are able to do etching, deposition, and this and the property of the plasma will determine, okay, the type of coating that we are able to put, or the type of removal of atoms from the surface that we are able to do. And here it's a really nice picture that I think it really crystallized the effect of plasma on the same material. So we can change if you want something which is highly reflective. For example, we want to use the B. If you want to have something which is poorly reflective, we want to use C, etc., etc., etc. So all the properties, the surface properties of materials, are modified depending on the plasma properties that is creating or removing them. The second application that I would like to talk about is medical plasmas. This is not very old in terms of progress, but here the idea is that to use an ionized gas, as you can see in this very nice picture, in order to treat the surface or to treat various elements which are now not, they are living elements. So, for example, it's called the cold atmospheric plasmas are used for viral tissues, to make a person look younger, which is not a bad idea. Besides therapeutic, it's also used for surface modification, for biological decontamination. So you can remove the contamination by applying a plasma, because a plasma is really a high temperature. So whenever you're gonna bombard it with is going to kill it. But at the same time, it's not like it is a fire, okay? Because fire, it is high temperature, but also it's high density. In this case here, when we are dealing with plasma, we are dealing with very high temperatures, but at the same time, very low density. And this enables us, so if we have a bacteria or a fungi, as shown here, which is sensitive to temperature, you are able to kill it, to destroy it, without actually changing effectively the temperature of the underlying substance where these things exist. So now we have a potential in cancer therapy are currently explored highly in a quite strong fashion in the United States. The goal here is to selectively ablate cancer cells while corresponding normal cells will remain unaffected. Again, by tuning the type of plasma, so basically the temperature and density, we are able to, if assuming to have the normal cell is able to sustain, let's say, a bombardment of 50 degrees Kelvin, 50 degrees centigrade, and the plasma can reach up to 55, and this will be able to kill the cancer cells without actually touching the normal cells. Okay, let's go a little bit bigger. So you guys all know neon lights, I think. But here I would like to highlight, so in the neon light, of course, what's inside is a plasma, okay? And it's generated by a potential difference between the two plates and by the neon or the type of gas that is put inside these tubes. Now, the way it's done is that it is we have a coating which transform the radiation of the plasma into something which is much closer to what the eye can see. Now we may say, okay, I mean, we have almost in all offices and all our houses, we have neon lights. So what? I mean, is this an active research field? And I would say yes. This is a high. There's a lot of activity in plasma generation, in light generation using plasmas, because this wide usage of the wide usage of these neon lights. If we are able to, let's say, to save, let's say, 1%. Or 2% or 0.1%, when you multiply this by the large amount of these lights that are being used, then a lot of savings can be made. Okay, let's now try to go further and discuss plasma thrusters. You can see that this is no longer there, but this is a space shuttle. It's no longer there, but I see the nice thing is that you can see clearly where the thrusters are. Now, I don't know if they are really plasma thrusters, but they could be plasma thrusters, okay? And so what's the idea here? If you know that when you would like to have a thrust, okay, the thrust is proportional to the mass that's being ejected and to the velocity at which it's being ejected. And what is best than to have a plasma where the thermal velocity is about 1,000 times of the background of the normal of high temperature, say gas or fluid or solid. So it is extremely efficient, and of course it's being explored all over the world about how to make these plasma thrusters, including actually at AUB in my group. We are trying to do some work on this. So this is for space travel. What's the idea? The idea since that, okay, so when you want to travel to space, you want to minimize the amount. So because the amount of gas that you want to bring with oneself to space is a load, and it costs a lot of money. So if we are able to bring something which is very light, but on the other hand, we have a plasma which is very hot, so we can basically compensate and even reach better thrust properties, even with just normal engines. So what you see here, this is something called Casimir, and you see that you have to the left, you have a bottle of gas, as simple as that. And then there is a first antenna, which is a helicon source, which is linked to a helicon RF generator, which produces the plasma. And then we have another antenna, which basically is going to heat it up, so to achieve higher temperatures before it's being expelled into space, and thus pushing the spaceship on the other side. Now, Dr. Abdul mentioned that we built a linear plasma device at AUB. This is the linear plasma device that is operational at AUB. You can see these are the magnets that were built in Lebanon. Okay, and this is the vacuum chamber, and we have something which is extremely similar to a helicon coupler. So we use a helicon coupler to generate our plasma and to study its properties in terms of efficiency and in terms of turbulence and instabilities that were mentioned before. Now, being in space, let's continue a little bit talk about plasma physics and applications. For example, this is the aurora borealis, which happened in the northern pole and would definitely affect our life here, and basically, and more importantly, affects the artificial satellites that we launch into space. Okay, and so this is what's happening here. Is basically that's a plasma which is being created at the upper atmosphere because of the plasma wind, and which interacting with the Earth magnetic field. And so when the plasma comes in, it will interact with the gas and generate these what we call northern lights, and they are very pretty but they are also very important to understand. Just to mention that northern lights don't only exist on Earth, but this is one on Jupiter. You can see that also give us some idea about the magnetic field structure on Jupiter, which, as you can see, there you have a North Pole, and you can see these aurora borealis that are occurring on Jupiter. So this is very important. Okay, now let's move on to something a bit bigger, which is basically what we call space weather. I think that most of you are aware that now there are people who are like the weather predictions on Earth. What they try to do is to do weather prediction in space. Why is that? Because when the sun sends us a large amount of highly energetic electrons and ions, they interact with the Earth magnetic field, which is actually protecting us, and they are able to deplete it. And by depleting it, they are able to provoke massive cuts in power or disrupt artificial satellites which are on Earth orbit. You can see here how it interacts with the Earth magnetic field. It changes it, okay, and then this really is extremely important point for our for our livelihood. Let's go further at a bigger scale. Talk about the sun. The sun, as you guys know, this is a fusion reactor. That's the biggest fusion reactor, okay, that we know of, and it's natural. So plasma physics in the sun is extremely important. But furthermore, it's being even more important by some observation. If you look at this graph here at the red curve, what you see is that as we move away from the sun, that's the red axis. The x-axis gives you the distance from the sun surface. Okay, and as you move away from the sun, instead of the temperature going down, actually the temperature goes up. It remains constant before going back down. And this is a big mystery that a lot of people, including here at AUB, we try to work on, and we worked on it actually in the past. Now no one is working on that at the moment, but it's something extremely interesting and important. Finally, I would like to go into what we call the interstellar medium. So basically, what you see with your own eye, this is plasma, and actually, it is believed. I mean, it's not believed. It is considered that plasma form 99% of the visible universe, and that's, you can see the reason why is that this is a region where you have plasma, which really interacting, giving light, and thus, for example, you can see here you have generation of stars in this region here, or in this region here. So it is quite important. Okay, in the summary, we went from a nanoscale of plasma applications, which is basically the plasma etching and plasma deposition, into nebulas, which is 10 to the 12 meter. So from 10 to the -9 meter to 10 to the 12 meter. Now, and this is going to give me an introduction to my second part of this lecture, which is basically about fusion. So fusion can occur in the sun, but can also occur at the millimetric scale in a tokamak. So what is fusion? Fusion basically is when you have two nuclei that are interacting with each other and generating different nuclei. Okay, so in this particular example here, which is of our interest, we have a deuterium, which is an isotope of hydrogen, and a tritium, which is another isotope of hydrogen, that are colliding with each other. Okay, and they form a substance which is highly unstable, and that which on its own bring a neutron at 14.1 mega electron volt and helium-4 at 3.5 mega electron volt. And so this generates a huge amount of energy, okay? And this energy, basically, it comes from the difference in mass. So the mass of the helium and the neutron, which are the product of nuclei, is actually greater than the individual mass of, smaller than the individual mass of deuterium and tritium. And the difference in this mass multiplied by the speed of light squared gives you the amount of energy that's being generated. So this is what people are interested in. Of course, it's definitely not only confined into deuterium tritium. We can take any two nuclei, and they have their they can make fusion, but of course the energies that are required will be much higher. Okay, so what are the different concepts of fusion? Well, we have the gravitational fusion, which basically occurs in the sun. That's what's happening in the sun. And we have inertial fusion, and then we have magnetic fusion, which I will be discussing a bit more. So let's just speak on about what's happening in the sun. The sun is a ball of fire, so a priori it should explode as any state when you have very high pressure, which is enveloped by extremely low pressure. So the space has no particles, so extremely small pressure, and the sun is extremely dense and extremely hot, so it's extremely high pressure. So a priori, the thermal pressure should tend to explode, to have its radius increase, okay? But on the opposite, we have the gravitational force. So the gravitational force will put it together, okay, and will result to the present shape that it has today. And this is actually, this interplay between these two forces makes some sort of an equilibrium, or will define the lifetime of a particular star. So now let's move on to the inertial fusion. So the inertial fusion is that you take a small tiny beam, which is seen here. Okay, you put it into this type of confined space, and then you shine a huge amount of energy, basically photons, into this space here. What it will do, it will implode it, and by imploding, so basically by going smaller and smaller, it will reach the conditions to have a fusion reaction, and thus it will produce a fusion reaction. The problem of this type of research, usually it is done for military purposes because it's really done once, it's an explosion. And the time between two shots in order for the laser to be ready is extremely long presently. Of course, things can change in the future. Now let's talk a little bit more about a magnetic fusion. So basically, the magnetic fusion, what's the idea? The idea is basically what we're going to do. We are going to make a plasma. So a plasma is something which is extremely hot, okay? 1 kilo electron volt, 10 kilo electron volt, okay? Extremely hot. But since it is formed of electrons and ions are so nice to follow the field lines, the magnetic field lines, then what we're going to do, we're going to build a magnetic field line, which is basically a torus. As you can see here, it's actually rotating. And by rotating, it is basically, even though it says a high temperature, relatively high density, but it remains confined to a given space region. Okay, so that's the basic idea. Now, in a tokamak, of course, you want to build something. It must have an equilibrium. Okay. Now, in the tokamak, the magnetic fields are relatively simple. So basically, you can see these blue coils. Okay, they generate a magnetic field which is toroidal. Okay, so basically going like this. But you also have the green coil. It's not coil. It's a solenoid. Okay, this green solenoid will generate a toroidal current, and this toroidal current will generate what we call a poloidal current, a poloidal magnetic field. A poloidal magnetic field, which makes, you can see that these the black lines, these are the field lines. So basically, a particle will follow according to this field line, and so it is confined. It is really a priori the zeroth order. It has what we call an equilibrium, at least. Okay. Now this system can get out of equilibrium, but at least to the zeroth order, there's an equilibrium. And this is why the tokamak is such a powerful tool or powerful idea, is that actually from a design and engineering perspective, okay, it's really simple. You have one solenoid and a couple of coils, and you can build these other toroidal, these other coils, but they are just simple. They are just round, okay, in order to achieve an equilibrium state. Now, I would like to talk a little bit a different concept. It's not only the only concept we use. Accelerator is another concept which exists, and now we don't have a current, but the magnetic field is twisted in such a way that it has a component which allows to have an equilibrium. Because once again, you want to build something which is basically in equilibrium. This is the major difference between what we call a tokamak and, for example, Polaris, the plasma device. The linear plasma device, there is no equilibrium. So you're constantly feeding in and removing, but there's no equilibrium. But here you do have an equilibrium. And so, as I said, this equilibrium is either done by simple magnets, but with a current in the plasma, or without a current, but with a complicated set of magnetic coils. I have been to Wendelstein 7X, which is in Germany. And believe me, this is the most complex machine that I have ever seen. So it's really huge. Okay, so what do we need to do to get a fusion device? Well, first let's try to understand what happens. So you have two ions, let's say deuterium and tritium. They're going in opposite directions, of course, but basically they go in all directions. But let's take those who are going in opposite directions. Okay, and if the conditions are fine, then they will interact with each other, producing the fusion reaction that we're talking about. But this is simply is a probabilistic approach. So not every two deuterium and tritium will interact with each other. You will have a fusion reaction. Okay, there's a probability, and this probability depends strongly on the temperature. So you can see that we must be at least about 10 kilo electron volt, from 10 to 50 kilo electron volt, so that we are at the highest probability of achieving a deuterium-tritium nuclear reaction. Okay, and this is extremely important because this is, once again, you see the x and y axis. These are a log scale. So let's say if you go from here to here, that's a factor of about 50. So it is really extremely important to get to the right temperatures. So clearly, temperature is a major player into the fusion reaction. Okay, but it's not only that. Of course, you want to have density. If I have two nuclei colliding, they will produce a lot of energy, but the number is one. I don't have many. I must have as many as I can, and this tells me that my density, my plasma density, must be really relatively high. Okay, so this brings us, if you do some mathematics, with something called the Lawson criterion, which tells us, let's say on a zeroth order level, what are the main three players for energy to start to be productive. So basically, so that the energy that getting out of the tokamak is at least equal or greater than the energy that you put into the tokamak. Okay, so that's the what you call the triple product. So I must have high density. I must have high density, so to have multiple nuclear reactions. I must have high temperature, so that so the two nuclei can actually produce fusion. And there is a third component which is called the energy confinement time. The energy confinement time, if you assume that you have a box, okay, and you have particles that are really trying to collide with each other. If these bugs, they are going into space, they will not have the possibility to meet and to fuse. Okay, so they must be confined, and thus we have what we call a confinement time or an energy confinement time. This means that the particle must remain in a certain physical space, at least as let's say 10 millisecond or 100 millisecond, so that you have the probability to have a fusion reaction. So this is what we call the Lawson criteria. Now, what determines this famous tau E is basically turbulence. And that's what Dr. Ali was referring to. This is what you see here. This is a simulation, okay? And what you see, this is a contour plot, what you call a contour plots of different perturbation that you can see that are growing, they are increasing. And this turbulence, what it will do, it will make it easier for the particle to escape the confinement zone. And since we don't want it to make it easier, then the problem of understanding turbulence and controlling turbulence is of prime importance. Now, I would like to show you a movie from a tokamak called MAST, which is in the United Kingdom. But it shows, it really is I hope is going to be interesting for you, because it shows you the globality of the thing. So this is the time you can see here, and you can see the startup. Okay, you can see the startup of the plasma. This is what we call the center stack. That's the middle of the tokamak, and this is the donut shape. Okay, and notice now what's going to happen at the edges here and here, with how it's interacting with the center stack. Okay, and now it's going to become more and more stable, and so the plasma now will reach. You can see what you have seen is that the center stack becomes actually darker over time. You can see it. I'll try to see if I cannot stop it. Okay, so you can see there's bright here in the middle, and with time you have a much more stable plasma, so it gets out. And then now here, the most of the light is coming from these regions here, what we call diverter region. And you can look at the outside here. You see the particle getting out, and then now you're going to have what we're going to call a disruption. So really, it's an abrupt termination of the plasma. So what are the challenges in this? How am I on time? Okay, yeah. What are the challenges that are met? Of course, there's really a lot of challenges. But here I'm just citing a few. Well, first, you must have higher density. So really, being able to produce plasma with higher density is a major research area. The other point, achieve higher temperature plasmas. What happened is that in a plasma, if you have a copper conductor, okay, and the copper conductor, the temperature increases, the resistivity increases as well. So the ohmic heating will also increase. In the plasma, it's the opposite actually. So the resistivity will decrease if the temperature will increase. Consequently, if we want to reach higher temperatures, we cannot rely on ohmic heating. Okay, we have to supply our own temperatures, and this is another major development area. Better confinement, so that's the third part, tau E. So on the macroscopic level, we need to understand turbulence and try to reduce it, and that's my topic. Of course, that's what I work on most of the time. And of course, at what you have seen in the movie, that you have this disruption. This is what we call a major disruption, okay, or major instability. And of course, for example, for ITER, some simulations would predict that if you have one major disruption in ITER, that's it, done. To give you a small story, so if you are in a tokamak, working in a tokamak, the tokamak exists probably 200 meters away from you, and there is like 2 meters of concrete around the tokamak, so that the neutrons do not affect you. Okay, but when you have a disruption, you can still hear it. It's basically, the whole thing goes up and down, and it's really extremely violent. The third part that I would like to talk about is really the adequate plasma phasing component. What I've shown here in this picture on the below is that the plasma, there's still some places, okay, where the plasma is going to interact with solid objects, and this is a major issue. Okay, this is a major issue. So what we need to do is really find out what are the materials that can be used, the pros and cons, because there's no magic material. Okay, but this is really a very active research area. Assess the effects of neutrons on its environment. So in a fusion reactor, as I said, you're going to have neutrons, and these neutrons will go and interact with the medium. For example, if you have a high temperature superconductor, they will interact with it, and so you will need to understand how the neutrons will affect this high temperature superconductor. And they come to it, so we need to impurity controls, etc., etc. So there's a large list, there's a long list of really important challenges that are faced in the fusion community, with the fusion community. So the last part of my talk is about the Arab Fusion Energy Initiative. So if you look at the map of the world, okay, you can see that, for example, if you start from east to west, you go Japan, Korea, China, Russia, the European Union, and the United States. They are all involved massively in fusion energy research and now fusion energy production. So basically now ITER is being built. India, sorry, I missed India, which is also involved. Okay, and so this is really a major issue. This is a strategic issue. Okay, for the world. Why? Because if we are able to achieve that, then the deuterium and tritium are relatively we are relatively able to find them or produce them on Earth and beyond. Okay, and we don't produce any gases. Of course, the tokamak itself or the stellarator itself will be radioactive, but at least this is very friendly with respect to the environment. So, despite large amount of research and development worldwide, this critical activity, I would say strategic activity, is definitely absent in the Arab world mostly. Okay. For this reason, we have several persons that who who came up together and tried to form an initiative. And this initiative, we try to define what are our goals, what is the best way to enhance fusion research in the Arab world. Okay. And of course, we will need to engage with governments, universities, etc., and private sector to advance in the field of fusion. So the various fields, if you say that probably I have 5, so basically 5 units to the left and 1 unit to the right, which is the most important one. So of course, we need to do some education and training, enhance education and training. Education, I mean, not only educating students, but most importantly, hiring professors, hiring researchers, and put them into the Arab world. That's very important. There are very few in the Arab world of researchers and professors in this field. Coordination among Arab governments and universities, engage the private sector, and also what we thought is that if we are able to build a center or an agency which will really centralize a little bit, okay, the research activity. Because if you want to build a tokamak or a stellarator or any other fusion device, this is really, guys, a huge amount of funding, but also a huge amount of human resources, okay? And so we cannot continue to be dispatched across the Arab world, each one of us in a given spot, not interacting with each other or not working with each other. And basically, by the way, this same concept applies in all fields, not only in fusion. Okay, it applies in all fields. So what we thought is that having this Arab Fusion Energy Agency is extremely important and will have at least the hope or the possibility to progress at a rapid pace, because we will be definitely competing with the US, with Europe, with China, which they are already far off. They are already begun a long time ago, and they have a lot of human as well as financial resources. Okay, so this is why we have this Arab Fusion Energy Agency, which is a plan. Our plan is to have it under the Arab Atomic Energy Agency, which is under the Arab League. So the idea is not to have this project to be basically pioneered by one state, let's say Lebanon or Egypt or Jordan, but really to be under the Arab League and to form the center, attract people, and start building knowledge, start building training professors or researchers or even technicians, very important. And we have the support of the IAEA, Eurofusion, ITER, and Prince Hassan of Jordan, and of course my university, okay, among other institutions. So what's the idea? As I said, the idea is really to have a center or multiple centers. Of course, this will depend on the funding, okay? But the main idea is really try to centralize this activity. And the way I personally imagine it is that you have people from, let's assume that the center is in Saudi Arabia. It can be anywhere in the Arab world. Please don't take this as you know. For the moment, there's no place really dedicated for this. So just an example, okay? So people from Lebanon, from Egypt, from Tunis, they will go to Saudi Arabia. They will live there. Like for example, people working for ITER. People working for ITER, they come from all the planet. They go from India, from China, from Japan, and they will all go to France and work in France. That's the idea. So countries will be glad to have that fusion program also, not only relying on the center, but definitely the center will speed things up. And so what the center will do? Well, it will seek funding to support the various activities. It will assist the development of national and regional research program, engage with universities, research centers, governments, and industry, assist in training, initiate and manage construction of fusion device. We do definitely need a fusion device so that we concentrate all our efforts into one thing, or let's say 2 things. But for the moment, let's get one thing running at that, and I think that I will be happy with it. And then, of course, coordinate them among the Arab institutions and manage international collaboration. So, in summary, I hope that I have been a bit probably superficial in what I presented to you. I did not know, once again, the background of the various people coming to this event. So first, I wanted to highlight that plasma physics touches on a variety of fundamental and applied fields, ranging from nanoscale to 10 to 12 meters. Fusion is an important, very important, I would say, opportunity to have a green, clean, and limitless source of energy that can be obtained not only on Earth, but also if you are on Mars, you can do the same. You have the same type of material that you're going to need, and this material exists everywhere in the universe. Hydrogen, basically, it's everywhere. And a third point that I wanted to highlight is that the Arab Fusion Energy Agency will be a unique opportunity for Arab scientists, one, to team up, to act together, and two, to join the world in the quest for a better future. Thank you all.